Hi everyone, Mr. Allen here. I just want to quickly go through, well, we'll see how quickly it ends up being. I tend to babble a bit. I want to quickly go through basically a summary of what we saw doing the investigations for characteristics of polynomials. So this is the solution or the set of answers that I posted. And first thing I want to say, the last thing I actually want is for you to try to memorize this somehow. These were general observations we had, or I had specifically maybe. And what I'm hoping is that with an understanding of how polynomials work, we can get these answers when we need them. It's pretty rare you'll ever be asked to give general observations about all kinds of polynomials, but of course the idea would be that I should be able to pull out any of this information for any graph that I happen to look at. So, just based on what we saw, the the general appearance, let's say, of the various polynomials. Straight line from grade 9, of course, starts down here, goes up here, starts up here, goes down here, might go horizontal, might go vertical. A second degree polynomial, a quadratic, we have basically the parabola shape, and again, it could be facing opening up or opening down, depending on whether our first coefficient is positive or negative. Again, though, not something that I necessarily need to memorize. That one you probably have already. But if you have an understanding as we go through this, you'll start to be able to pull these things out for yourself. So if we think of this as just this is what a parabola looks like, this is what a quadratic function gives us, we should be good. Cubic, so here's our basic shape, quartic, kind of like a W, quintic, and a sixth degree polynomial. And the big thing to pull from this is my straight line goes one direction, whichever direction it happens to be. Again, it could be from up here in the second quadrant down towards the fourth. It could be completely horizontal, but it goes one direction. It has a degree of 1. The quadratic has a degree of 2. X squared is the dominant term in this function, whatever the rest of the values happen to be. And it goes down, then up, or up, then down, 2 directions. Cubic, 1, 2, 3 directions. Quartic, 1, 2, 3, 4 directions, and so on and so on. And so what we can pull from that is that the number of different directions any polynomial can travel is equal to its degree. Another way to say that is the number of times it can turn, or the number of turning points it can have, is basically one less than the exponent. Okay, so again, here I have an exponent of 1, y equals mx plus b. I can turn 0 times. An exponent of 2, turn once. Exponent of 3, turn twice, and so on. That also means that, in sort of the wording again, turning points, local max min, the number of maximum or minimums, the local maximum or minimums I can have, is 1 less as well. So with my exponent 2, I have 1 low point. With my exponent 3, I can have 1, 2 local maximums or minimums. With the quartic, I can have up to 1, 2, 3, and so on. So if we just kind of look at a couple of these, pull up this one specifically. This is again sort of the general shape of our cubic equation. The key here, though, is what happens in the middle is based on the rest of the expression. So if I take that out entirely, you see that sort of the middle is pretty flat, not a lot going on there. When I put this back in, I get varying, that was a bad choice, varying, that's what I'm trying to do, varying heights for my local maximums and minimums. And of course, as these values become larger or smaller, they'll make more or less difference on the graph. And the reason for that is kind of an important one. And it kind of leads to this end behaviors thing that I tend to get more questions about than anything else. The general form of any of these expressions is always based on the main term. The x cubed gives me this basic shape, and then with some other stuff and with some other values in here, the middle section gets, again, a bigger or a smaller peak or valley, maximum or minimum. But the general curve is established by this. Similarly, my fourth power is based on this primarily, and then the secondary numbers make that middle section bigger or smaller. And the reason for that is basically the dominance of the terms. So what do we mean when we say dominant? We already talked about how in the middle of our graph here, with values around -1, -2 in this case, the non x4 terms are the ones that really establish what goes on. When we get to different numbers, so let's kind of pull this up in an Excel spreadsheet. What I've got here are different x values, -1, -0.5, and so on, that are around 0. And what you can see is if we calculate each individual term, so this is the x to the fourth term, this is the -6x cubed term, this is the 3x term, the resulting values of y are more affected by these in this area. So sort of if we look specifically, we have an answer of 4, this is a 1, this is a 6, -3, all similar numbers, but still this value is noticeably larger than the x to the fourth term. As we get closer to 0, 0.75, -1.5, those two values add to -0.75, which is quite close to this. The x4 term has very little effect. If we sort of stretch these out, what you'll see is that these strange looking numbers here, again getting closer to 0, x to the fourth is now really insignificant. This x cubed term is actually quite insignificant as well because my value of y is almost exactly just what the 3x term is. So close to 0, taking things like doing larger exponents on values close to 0 gets us values that are even closer to 0, and of course the smaller exponents are the more important ones. Now, as we go out, this will change for us. So let's just pick a couple of numbers here that are towards the sort of moving to the left. And as we see -2, at this point our most important or most dominant term is the -6x cubed term. There's 48, this is only 16, this is only -6. We go a little further out, similar, they're getting closer together. -6, we actually get the two terms being exactly just as valuable one as the next. And then -8, of course, the x to the fourth overtakes it and starts becoming larger and larger and larger. Relatively speaking now, at -12, the x to the fourth is about twice as big. And then if we actually get to a point where we're going significantly further out, what we see is the x to the fourth again is getting bigger at a faster rate and getting to be more and more significant compared to the other one. And then if we just kind of go, I don't know how far I can go here without breaking things. Maybe that's a good place to go right there. Okay, so I just changed my expression slightly here. So it's x to the fourth minus 6x squared now, plus the 3x. And you can see that at -100, this number is 1, 2, 3, 4, 5, 6, 100 million. The result of adding these all up is just shy of 100 million. And so the further we get, the more significant this is relative to this one. And now basically these two numbers are almost insignificant. you can see that my x squared, x to the fourth value is almost exactly the same as my y value, and these are just kind of falling off. So all that to say that the dominant term is the one that's influencing the graph the most. With any of these expressions, with any polynomials, the term that will influence the values the most as our x values get extremely large or as they get extremely small, so things like negative 1,000, negative 10,000, positive 1,000, positive 10,000, the first term will always be that dominant term. And that's why our graph of x to the fourth will always eventually on the outside continue on up towards infinity on both the left and the right. Because no matter what's in here, it's not going to be significant as the x values get large enough. So essentially, those two ideas, that the exponent determines the number of changes in directions I have, or the number of directions I can go. My exponent is 6, I can go 6 directions, up, down, up, down, up, down. And then the idea of the end behaviors being established by that dominant term. The x to the fifth decides where I'm going when my x values get large. It doesn't matter how many x to the fourths I have, x cubes I have. X to the fifth with large numbers will get far more significant, and the rest of it doesn't matter anymore. Will allow me to determine whether I'm starting down in the negatives or up in the positives based on that one term in the front. And everything else can be kind of determined from there. If my graph is an even function, I will have a minimum value because it looks like this or like this. So it comes down to a certain point and then goes back up, or like this. It comes down to a certain point and goes back up. If my dominant term is negative in the front, then there's a maximum value. It's exactly the same thing. I know the basic shape based on my end behaviors, and there will be a highest possible point I get to. If I know what my odd functions look like, basically, then I know they start on one end and they move up towards the other side. And so that means that there will be no maximum, no minimum. There'll be local maximums, local minimums perhaps, high points in this general area, bumps, if you will, but there is no maximum value. This graph will continue on forever in both directions. And again, I can determine those things simply by knowing the basic shapes of my graphs and then by thinking about it. Domain, all x values are possible, of course. Range, again, with the evens, there will be a minimum or a maximum depending on what it is. And then the end behaviors, as we said, they are kind of the key concept here, that if I put a big number in for x, if I put in a large negative value for x, I can determine what happens on my ends. And from there, the rest of the graph will come together. So, a little bit more babbling than I intended, but hopefully it'll reinforce anything that you saw and you didn't recognize or that you weren't too sure about. Last comments here, when we get that negative coefficient, again, doesn't make a big difference, so we don't need to sort of memorize what happens with the negative coefficient. We simply need to remember that what happens with that first term is important now. So if I have an x to the fifth, but oh, wait a minute, there's a negative sign in front of it, that means that whatever I had, negative 100 to the exponent 5 is a huge negative number. Oh, but wait a minute, there's a negative 2 in front of the actual x to the fifth term now. So that means I'm going to basically flip my graph. Same sort of thing with the evens, of course. The whole graph flips. And so now instead of having a minimum possible value, I'll have a maximum. But otherwise, the graph is basically the same. It's not a W anymore for a fourth power, it's an M. Okay, everything else stays the same. So hopefully that will reinforce some of the concepts and allow us to move forward from here. Good luck.